Just in one problem here, we're covering almost all the learning targets that are important in Unit 2. So graphing a polynomial, that's part C. Use the rational zeros theorem to find the zeros, that's pretty much part A and B. Now, solve a polynomial equation. I want to talk about this learning target. I didn't include a question like this on Unit 2 exam. But because the department put it here as an important learning target, I want to make sure I cover this. A polynomial equation would be something like this. So I'm going to kind of veer off from question 1. So this would be a polynomial equation. What's the only difference between that and what we're doing here on question 1? It's equal to 0. This is called a function because it's in function notation. This is a polynomial equation. Guess what the steps are to solve a polynomial equation? Same. Okay? You get it equal to 0, and then you factor. This is just like a quadratic. If this were x squared minus 7x plus 6, and let's assume that it factored, what would you do to solve a quadratic that equaled 0? You would just factor. How do we factor things that are bigger than x squared? We do this. We use the rational zeros theorem to factor the polynomial. So whether you're asked to sketch the graph of a function that's a polynomial or solve a polynomial equation that equals 0, it's the same steps. Does that make sense? I want to make sure we're on the same page there. Okay? Rather than p of x, we have a 0. But where would you go from here? Well, you still use the rational zeros theorem. What is the rational zeros theorem? Synthetic division with p and q, right? And then you test those. Once you find some that work, you can write it in factored form. And then once it's in factored form, you can find your solution. So that's what it means to solve a polynomial equation. You just get it equal to 0 and go through these same steps. Now, for question 1, we're not solving an equation. We're actually graphing a function. So, step 1, use the rational zeros theorem. Or for part A, use the rational zeros theorem. So factors of 6, that's going to be values for p. Factors of 1, that's going to be values of q. So p divided by q is plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. I gave you a few minutes to work on it. Anybody find any of those that worked?
1.
Positive 1? Positive 1 works? All right, sweet. That's usually what we start with. If 1 didn't work, you would just move through that list, right? You would try probably negative 1 and then plus or minus 2. Plus or minus. You got to go through this to find. Now, we haven't had a discussion on this for a while. Are these all the solutions in this list? All the zeros, I guess? Are they in this list here?
Yeah, the real ones.
Close. You're close. Not just real. It's even more specific. Rational. Rational numbers are numbers that can be written as fractions. The square root of 2 technically is a real number, but it's not a rational number because it can't be written as a fraction. So if there are rational zeros, they come in this list. How many zeros are there total for question 1? 3. And it's no guarantee that all 3 of them come from this list, only the ones that are rational. There could be irrational zeros, there could be imaginary zeros, but if they're rational, they're going to be from this list. So let's see, 1 sounds like it works. I put a 1 for the x cubed coefficient. I put a 0 for the coefficient of x squared because it's not there, remember. A negative 7 for the linear coefficient, and a positive 6 for the constant. Now let's test it. And it does. It works. So what we've done is prove a couple of things. We know that x equals 1 is a 0, but that also means that x minus 1 is a factor. So if we were to write p of x in partially factored form, it would be x minus 1, and then x squared plus x minus 6. Is that fully factored? No. How do we know that's not fully? Because part B is to factor the polynomial. If this is what you write for part B, factor the polynomial, you'd get it marked wrong. It's not fully factored. Why not?
You still have to factor the x squared.
We still have to factor this. The rule is, how many factors do there need to be for this polynomial? 3 factors, because it's a third degree. Yeah? So we have 2 factors. One of them is quadratic. That means this either needs to be split down using factoring. And if we can't factor this, What's the other option? Quadratic formula. So hopefully it factors. This one does. I don't know if number 2 factors, but this one does. X plus 3x minus 2.
Really quick, how did you give x equals like that equation? How did you?
So because 1, we got a remainder of 0, which means 1 is a 0. X equals 1. If x equals 1, that means it came from a factor of x minus 1. Does that make sense?
Maybe.
Like if we were to solve a simple quadratic equation like, well, just x squared plus x minus 6 equals 0, the way we would solve that is by factoring, right? And then what are the solutions, though? Those are the factors. What are the solutions? X equals negative 3 and x equals positive 2. So what we're doing is just going backwards. If we know that x equals 1, then we're just putting it into a factor like that.
Gotcha, and then when we have like the bottom part of the synthetic division.
The bottom part is x squared plus x minus 6. That's what those numbers mean. Does that answer your question?
Mm-hmm.
Okay. All right. So that answers part B right here. So we have part A, which was using synthetic division. We have part B, which is factor the polynomial. Part C is to sketch the graph, showing intercepts and proper end behavior. That's a gigantic graph. There we go. Well, the whole reason we had to go from part A to part B is to write it in factored form, because without the factored form, we wouldn't know what the x-intercepts are. We could have found, well, let me ask you this question. In general form like this, what intercepts could we have found straight up without having to factor it? When I say intercept, there's x-intercept and y-intercept, right? How do you find the y-intercept?
Let x equals 0.
Let x equal 0. So we can find the y-intercept simple enough from general form. What would the y-intercept be? 6. What we can't find are the x-intercepts when it's in general form. We have to find the x-intercepts from factored form, because how do you find the x-intercepts?
When y.
You let y equal 0, which is exactly what I was talking about with solving a polynomial equation. If y is equal to 0 and you had a big old fat 0 right here, wouldn't you want it in factored form like this to find what the solutions are? Okay. So what are the x-intercepts then? 1, negative 3, and positive. This is also the place to consider, if you don't remember, way back from Unit 2, not all x-intercepts cross through the x-axis, remember? What else could they do? They could bounce. So this is like I said, when we're going through these, it's okay if you can solve this problem, but you need to think about what all the different variations could be. If this was x minus 1 to the second power, what difference does that make? If there was an exponent of 2 right here, it means it bounces. What if this was x plus 3 and there was an exponent of 5? There was an odd numbered exponent right here. So what's the rule there? Even exponents, they bounce. Odd exponents, they go through. That's something to remember there. So the zeros are x equals 1, x equals negative 3, and x equals positive 2. The y-intercept we already decided was x equals 6. And the directions say showing proper end behavior. So let's talk about end behavior. The function itself started out as an x to the third. It's p of x equals x to the third. It's a third degree polynomial. End behavior means what is the left side doing, what's the right side doing? Is the left side and the right side both going up? Are they both going down? Are they opposite of each other? They're opposite. And the way that we know that is the degree is odd. If it was a fourth degree, they'd both be going up or both be going down. So the left side is going down to negative infinity. The right side is going up to positive infinity. What would have caused that to change?
Would be negative.
If there had been a negative in front of the x to the third here in the beginning, then the left side would have been going up and the right side would have been going down, right?
So that's just like the standard, like the left is down, the right is up, and if it's a negative, then it's opposite of
Correct.
that?
Yep, did everybody hear that? It's a good point.
Can you say it again?
And it's not just the standard for x to the third. The standard for any odd-powered function that has an odd degree, or odd leading the highest degree, is that the left side is going down to negative infinity, the right side is going up to positive infinity. If there had been a negative sign in front, negative x cubed, that's a vertical reflection, right? So now everything flips upside down. The left side would be going up and the right side is going down. Now both of these questions, 1 and 2, unfortunately, are both third degree, so the graphs are going to look similar. Again, though, it's important to think about what could be different. If this had said x to the fourth to begin with, what would have changed in this problem? If this were x to the fourth, what would have changed?
They'd both be up.
They'd both be either up or they both could be going down, depending on if there's a negative sign in front. That would also change the number of factors. If it was x to the fourth, how many factors would you need to find? 4 factors, which means there could be 4 zeros. Now, there might not be 4 distinct zeros. If they have multiplicity, then it may look like you have less, but they count as multiple zeros. Anyway, just things to think about, and that's why I say go back through your old exams, because you might have a question on your exam that was x to the fourth that could help you with that.
If it is an even exponent, is it like standard up or?
The standard is both going up.
So if it's a positive, it's up, and if it's negative, it's down?
Yep. Yep. We're almost there. What are we missing? We got to put the sides together, the left side to the right side. This is showing proper behavior of the function at each 0. Now, am I crossing? We already decided crossing or bouncing at each one of them.
Cross.
Yeah, we already decided that. So I crossed through negative 3. The grading rubric is also kind of specific, and we went over this for Unit 2 exam. If there's an integer value between zeros and y-intercepts, do you remember what we talked about here? It may not go straight to it.
Plug in those points.
You do need to plug in these negative 2 in it, because it might happen that it goes way up here and then down. So just for the sake of time, let's just plug in one of them, negative 2. If you plug in negative 2, I'm going to plug it into the factor form. Negative 2 minus 1, negative, let's see, negative 2 minus 1, that's negative 3. Negative 2 plus 3. So we have negative 3 times 1, it's negative 3. And then if I plug in a negative 2 here, man, that's negative 4. So it's negative 3 times negative 4. That's way up there. So it actually goes up to 12. So like way up there. So it comes up to 12, and then it comes back down like that. And then it crosses through at x equals 1. And because there's only decimal values between 1 and 2, I don't expect you to plug in decimal values. So just at some point it needs to turn back up, cross through at x equals 2, looks something like that.
If there's, so for example, negative 2 and negative 1 are both in between.
I'm only going to
You only have to.
just plug in 1. Yeah, and even though this probably isn't all the way up to 12, if you mark it as negative 2 comma 12, then at least it tells me that you've figured out what the value should be if it's way off the graph like that. What other questions do you have on question 1? Yeah, that's fine.
On the first part, part A, how do you write like rational roots? Do you do like x equals 1? Because like we have to factor it, right, to find the rational roots?
So use the rational zero theorem to determine all possible rational. This is actually the answer right here to part A. Those are all the possible rational roots.
Oh, right, okay.
Is that what you were asking?
Yeah,
So that's the answer to part A. Those are all the possible.
and in factoring the polynomial, does it want us to literally just have it like p of x equals x minus 1, x plus 3, and x minus 2? Does it want us to find x?
Now, that's a good question. If it had said factor the polynomial and list the zeros,
Oh, okay.
so this one just said factor the polynomial. But if it said factor the polynomial and list the zeros, what would the zeros be here?
The opposite of what's in negative.
X equals 1, x equals negative 3, and x equals 2. So you'd have to actually list those out if that was the direction.
So I mean, what you're saying is we have to, for part B specifically, you have to write out the x minus 1 times x plus 3 times x minus
'Cause that's what they're asking us to do is factor the polynomial. They could have said, instead of factor the polynomial, they could have just said list the zeros. So if they had said list the zeros, then you would just say x equals 1, x equals negative 3, and x equals 2. So it is important to read those directions. Make sure you're answering the question that's being asked. Yeah?
You probably won't get marked wrong if you list the zeros either way, right?
No.
Okay.
No.
I have one more question.
Yeah.
I'm gonna look is on like the direction of the arrows, so like, you're saying that if it is a positive leading coefficient, it's going down first and then up, and if it's negative.
Only if the degree of the polynomial is odd.
Okay.
So if it was an x to the fourth or an x to the sixth, then both sides are going in the same direction. Either they're both going up or they're both going down. That's if it's an even degree. Does that make sense?
Yeah, so odd, opposite?
Odd degree means opposite in behavior. And the normal there is that the left side's going down, the right side's going up.
And then even.
If it's an
is
even degree,
same.
and the normal there is they're both going up. Unless it's flipped upside down, then they're both going down.
Okay, and that would mean if it was like the same, but it's negative, they're down?
Right.
Okay, sorry.
Yep. No, that's okay. Those are all good questions. All right. Question 2. It seems like it's the same. The reason I put this one on here is part A is a little different because your leading coefficient is not just 1. So it does change how you list your possible rational zeros. So for part A, you would list P. I would do P and Q separate for this one. So the values for P are the factors of 10, which are plus or minus 1, 2, 5. Those are the factors of P. And then the factors of Q are the factors of 6, so plus or minus 1, 2, 3. So those are P and Q separate. Your possible rational zeros, though, are P divided by Q. That's what we really need to get to. I haven't done one like this in a while. So you take, the way I've instructed back in Unit 2 is you take one value of P and divide it by all the values of Q. So 1 divided by all of these, so it's going to be 1 divided by 1, 1 divided by 2, 1 divided by 3, and 1 divided by 6. And then you move over to the next value, 2 divided by 1, 2 divided by 2. So it's going to be a lot longer list for P divided by Q. So that's plus or minus 1, plus or minus 1/2, 1/3, and 1/6. And you don't have to duplicate. For example, 2 divided by 1 is not on our list, but 2 divided by 2 is just plus minus 1. We already have that. So you don't need to write the duplicates. So we have plus or minus 2. 2 divided by 2 is 1. We already have that. 2 divided by 3 is 2/3. 2 divided by 6 is 1/3, and we already have that one. So we just need a 2/3. And we have 5 divided by 1, 5 divided by 2, 5 divided by 3, 5 divided by 6. We need all of those. And finally, 10 divided by 1, we need, because that's 10. 10 divided by 2 is just 5. We already have that. 10 divided by 3, we need, but 10 divided by 6 is 5/3, and we already have that one. So we need a few more, plus or minus 10. We already have 10 divided by 2. We need 10 divided by 3. But we don't need 10 over 6, because that's just 5 over 3. That is a long list of P over Q. Yeah.
So if we were given this exact same question on a test, I tend to just put like plus or minus, and then I'll do like a comma, and then just do all the numbers. That way I don't have to write it every single time.
That's fine. I would understand what you mean there.
Okay.
Yeah. Any questions on part A? Possible rational zeros? We really haven't done many where we had to test a fraction, now that I think about it. We've always just tested whole numbers. We might want to test some fractions when we're doing synthetic division. I don't know. Maybe. But that's part B. This is part A. Those are your possibles. Part B, I guess it would be nice if they didn't have to test the fractions, but let's go through some of the whole number ones first. Let's test positive 1 and just hope and pray that positive 1 works. Negative 1? All right, I like your thinking. Negative 1. Now there are not any missing terms, so we don't have to put a 0 in any placeholders. Oh yeah, -1. What a good choice. Great suggestion. And you don't have to do this intermediate step. Whenever I find a 0, I just write that 0 as a factor. So if x equals -1 is a 0, then x plus 1 is a factor. And then the other factor is 6x squared plus 11x minus 10. Now, with question 1, we had a quadratic that was easy to factor. I don't know if this factors, maybe it does. If it doesn't, we use the quadratic formula, but 6x squared plus 11x minus 10. Well, 6 times -10 is -60. So we need two values. We need two values that multiply to -60 that add to 11. Actually, I think this works. 15 and -4, yeah. So 15 and -4, those multiply to -60, but they also add to 11, so it does factor. That's interesting.
Are we gonna most likely have one that doesn't factor, that we'll have to do?
There's a good chance, yes. And since you asked, what would we do if it doesn't factor? Quadratic formula. Now, knowing that they're wanting us to sketch the graph showing the intercepts, that kind of implies that all of our zeros are real numbers because we have to graph it. If they're just asking you to factor the polynomial or to find the zeros and not sketch the graph, then maybe your zeros are imaginary and it doesn't matter because you're not graphing. Does that make sense? But because they're asking us to sketch the graph, it kind of implies that all of our zeros are going to be real numbers. But to answer your question, yes, you may want to prepare to have some that use the quadratic formula. No. The only formulas on the formula sheet are those ones from chapter 8, which were the sequences in series.
If you learn the jingle, you like.
That's right. I'm not going to sing it though.
That's like, I always look at.
So we need to factor this. So I would do the factor by grouping method. That means the 11x gets split up into the 15 and -4. So 11x would be 15x minus 4x. This is the factor by grouping method. And then group the first two terms, and you can pull out a 3x. And then if you group the last two terms, you can factor out a -2. And it's really important, if you remember this technique, it's really important that those two sets of parentheses match. 2x plus 5 now is a common factor. So if you factor out the 2x plus 5, then you're left with 3x minus 2. So those are now your three factors.
So just so I make sure I have this right, so out of all of the PQ list, -1 is the only one that works out of all of those?
That's a great, I was actually just gonna ask that. What's the 0 from this factor? That was on our list. Okay, what's the 0? What's the 0 from this factor?
5/2.
Careful, you're close, not 5/2 though. -5/2, because you gotta subtract the 5. So it's -5/2. That was in our list, right? I think so, yeah. So what does that mean? If we had tested -5/2 with synthetic division, would it have worked?
Yeah.
Yeah. I'm actually really curious right now. You don't have to show this, but I'm going to.
Like a multiple of a factor, doesn't make it squared, right? It's just like, so we have like 3x, 2x plus 5, and then we have -2, 2x plus 5. 2x plus 5 is just like one of the factors, right? We don't have like squared or anything like that.
Yeah, we only have one of them.
Okay.
Because here, I know it looks like it appears twice, but that's because it's a common factor that you factor out. So this is the polynomial. This is the answer to part B right here
Right, okay.
in factored form. Now, it could be that x plus 1 appears again here like x plus 1, so that it appears twice. If you were to graph it, then remember it would bounce. So to finish this one off, we need a graph. Okay, so we have a 0 at -1. Okay, you gotta be careful on these. The 0 is -5/2. What is that actual number, -5/2? Yeah, remember those are decimals. When you're graphing, those are decimals. -5/2 is -2.5. And then the other one here, 3x minus 2 is gonna give you a 0 of 2/3. That's 2/3 of the way to 1. Right there. The y-intercept you could have got from the original form, the general form way up here. If all the x's were 0, you get -10 as your y-intercept. All the way down there.
Sorry, I'm a little confused by that. You're saying that the last number on that formula would be y?
Because how do you find the y-intercept of any function?
You switch x and y, right?
That's how you find the inverse.
Or, I'm sorry.
That's, yeah. To find the y-intercept, you set all the x's to 0. So, yeah, if all of these x's turned into 0, then you're just left with -10.
I see.
Does that answer? Now, if you don't have the general form, you could also find that value from factored form. If you let all these x's equal 0 and multiplied everything out, you'd still get -10.
Gotcha.
Now, the proper end behavior, this is also third degree, so that means that the left side is going to -infinity and the right side is going to +infinity. We just got to figure out how to connect all these. So they all cross through because there's none of those factors here have any multiplicity. None of the zeros have multiplicity, so they all cross through. Technically speaking, I guess, to be accurate, there is an integer value between these two zeros. The integer value is -2. So you are supposed to technically plug in that integer value. If you plug in -2, -2 plus 1 is 1. Let's see, -2, that's -4. -4 plus 5 is 1. What do we have over here? Let's see, -2, that'd be -1, right? So -1 times 1. So far we have -1. Now if we plug in a -2 here, that's 3 times -2. -6 minus 2 is -4. So here we had -1 times -4 is 4. So -2 comma 4. So it goes up to 4 down here all the way through your y-intercept. And then, whoa, close enough. It's supposed to go through that point of 2/3. Wow. Okay, we're almost there. Let's see if we can finish up this Unit 2 review and then we'll get out of here. Oh, mama. How many more questions do we have? I hope we'll finish this today. So this is from section 3.5. Given the zeros, you have to work backwards. Remember these? If you're already given the zeros, you got to work backwards. That means zeros turn into what? Zeros turn into factors, and then you multiply the factors together to form the polynomial. That's how these steps go. And boy, part B is an interesting one where it gives a condition like that. We actually did not do this in Unit 2. It's only one extra step. It's not too bad. Part A is kind of straightforward. If x equals -3, then the factor is x plus 3. Yeah? Now, with x equals 1 plus I, you have to remember that those types of zeros always come in pairs, so the conjugate pair is 1 minus I. But then you got to place those complex zeros as factors. The way I instructed it back in Unit 2 was you just move all the terms to the same side as the variable. So if you were to move these two terms over with the x, you're subtracting 1 and subtracting I. So it'll be x minus 1 minus I. And then if you move these two terms over, you're subtracting 1, but adding the I over. So it'd be x minus 1 plus I. So there's the factored form, but they don't want the factored form. It needs to be multiplied together because it says real coefficients. So now we get to multiply these together. I would suggest you multiply the two factors together that contain the imaginary parts. So multiply these two together, just using the distributive property. So x times x is x squared, and then we have x times negative 1, that's negative x. And then we have x times I, so that's ix. Then we have negative 1 times x, so another negative x. Then negative 1 times negative 1 is positive 1. And then negative 1 times I is negative I. And finally, negative I times x is minus ix. And negative I times negative 1 is positive I. And negative I times positive I is negative I squared. So if you have not made any arithmetic errors at this point, any term that has an I should cancel out. If that doesn't happen, then there's been an arithmetic error somewhere. Negative I squared also should cancel, but not because it cancels with another term. I squared equals negative 1. So you gotta be careful. If it's minus I squared, that means it's minus negative 1. So that turns into plus 1, right? Just be careful with your minus signs there. So minus I squared is really plus 1. And then the plus 1's add together to be plus 2. The negative x's add together to be negative 2x. So that really turns into x squared minus 2x plus 2. That we then get to multiply with x plus 3. Now there are no more imaginary terms. So multiplying those together is going to give you x to the third minus 2x squared plus 2x plus 3x squared minus 6x plus 6. Let's see, what are some like terms here? What are some like terms? That's going to become negative 2x squared plus 3x, that's plus x squared. And then 2x minus 6, that's negative 4x plus 6. Now, I kind of skipped over something at the beginning that's kind of important. I apologize for skipping over that. For part A, it says here's the zeros, but then it also gives a condition. The leading coefficient is 1. So this is something important to pay attention to. What if it had said the leading coefficient was 6? What would that have changed in the problem to begin with? If the leading coefficient were 6, you would put a 6 here, and then you would end up distributing. Does that make sense? The leading coefficient was 1. I just skipped over that, but that's important. And that's kind of what this initial condition here is for part B. But anyway, that's the answer for part A. Let's move on to part B. If I have room, yeah, I got room. Yikes. What degree is this? We got 1, it says degree 4. Okay, like I said, I didn't necessarily do one like this in the instruction for Unit 2. They were pretty clear on part A what the leading coefficient is. The leading coefficient was 1. It's not clear what the leading coefficient is on part B. So we can't assume that it's 1. Are you guys following this? We can't assume that the leading coefficient is 1. So then what do? Do we know what it is? So we need to put in a variable there to hold that place until we find out what it is. So I'm just going to use the variable a as the leading coefficient. Okay, but we still proceed as normal. All of these zeros are going to be placed into factors. So p of x, I'm going to put in a as the leading coefficient because I don't know what the leading coefficient is. But then we have x minus 2 and x plus 2. X minus I and x plus I. So there's the polynomial in factor form. And again, the reason that there's an extra variable here, a, is it was not explicit in the problem what the leading coefficient is. They gave us an initial condition, which we can do at the end. So we need to put in some random variable to hold the place of that leading coefficient until we find out. So again, multiply the two factors together that contain the imaginary parts. So if you multiply those together, you're going to have x squared plus ix minus I squared. So the ix and the negative ix cancel out. Minus I squared is really plus 1. So that's x squared plus 1. If we multiply the x minus 2 and the x plus 2, that's x squared minus 4. And then we still have the a in front. So we're getting closer. Now if we multiply the x minus 4, or the x squared minus 4 rather, and the x squared plus 1 together, we get a, we'll have x to the 4th, and let's see if we can do this. We're going to have an x squared and a negative 4x squared. So x squared and a negative 4x squared. So that's negative 3x squared. And then we have a negative 4 times positive 1, which is negative 4. Now, I wouldn't distribute the a at this point. Let's talk about what that initial condition was. The initial condition is that p of 0 was equal to 8. What does that mean?
That whole thing should equal 8 if you put 0 in x.
Did you guys hear that? Whatever's inside the parenthesis represents x. Whatever's outside of it represents what goes in place of p of x. So you're absolutely right. This can be replaced with 8 as long as x equals what? 0. So if I plug in a 0 for all of these x's here, then what do we have? Negative 4.
So a should be 2.
So what we have is 8 equals a times negative 4.
So that would be 2.
So then how do we proceed there? Say again?
A would have to be negative 2.
A would have to be divided by negative 2, so a equals negative 2. And what is that telling us?
The leading coefficient.
The leading coefficient now is negative 2. So p of x, and I'd be okay if you left it like this. Or if you wanted to distribute it out and make it negative 2x to the 4th plus 6x squared plus 8, that's fine too. I really don't mind at that point. Once you know what the leading coefficient is, you're good.
So it wants us to find, oh, okay, so it doesn't want us to find A, and then plug it back.
It wants us to find a so that ultimately we know what the equation is. There we go. Okay, so for part A, show and label the vertical asymptotes. Those are found by factoring the denominator and figuring out the values of x that are excluded from the domain, that x cannot be. And if your numerator is not factored, I would factor the numerator at the same time. Write the whole thing in factor form. So x squared minus 4x plus 3, that is going to be x minus 3 and x minus 1. So those are the two factors for that quadratic expression, which means the two excluded values are x cannot be 3, x cannot be 1. So on your graph, you would have a vertical asymptote at x equals 3. And it says show and label. What that means by label is x equals 3. You've just labeled that vertical asymptote. And then the other one, what was it? X equals 1. So that's the extent of part A, show and label the vertical asymptotes. Now part B, show and label the horizontal asymptote, if any. The horizontal asymptote, what was the function of it? The reason the horizontal asymptote is there, So the vertical asymptotes are domain restriction. The horizontal asymptote, do you remember what that one was for? It has something to do with the range in a way, not so closely connected to the domain like the vertical asymptotes. The horizontal asymptote is there to describe end behavior, so way out here as x approaches infinity, or way out here as x approaches negative infinity. That's what the horizontal asymptote is there for. But it has to do, if you forgot it, it has to do with comparing the degree of the numerator to the degree of the denominator. Okay? And if this is something that you're not as familiar with or don't remember, it's in your notes from section 3.6. So you might want to go through there and look at those again. But to find the horizontal asymptote, you compare the degree of the numerator to the degree of the denominator. If the numerator has a smaller degree, which is the case here, this is a degree 1 expression. This is a degree 2. If the numerator has a smaller degree, then the horizontal asymptote is the line y equals 0. So this particular problem has a horizontal asymptote of y equals 0. I think the next problem, number 5, is the what else could happen. So, for example, what happens if they're the same degree? I think that will be addressed in question number 5. But for this one, since the numerator has a smaller degree than the denominator, then the horizontal asymptote is y equals 0. So we have shown and labeled the horizontal asymptote. So part B is done. Oh, part C is a nice one, because finding the x and y intercepts is the same for any kind of function, not just rational functions. You do it the same for anything. How do you find the x-intercept? That's the inverse. To find the inverse, you flip x and y. To set y equals 0. And how do you find the y-intercept? Set x equal to 0. So that's how you find intercepts of any function. You just let x and y equal 0, respectively. So let's start with the x-intercept. If we want to find the x-intercept, we let y equal 0. Remember, f of x represents y. So if we set the whole entire function equal to 0, we need to solve that equation. And if you remember from our discussion, I know it's been a month or two, but there's actually a really easy way to solve this equation. You think, well, gosh, this is going to be hard because it's a rational expression. But what's the only time a fraction is ever going to equal 0?
If the numerator is 0.
If the numerator is 0, right? 0 divided by anything is equal to 0. So the only way that this rational expression is ever going to equal 0 is if the numerator equals 0. Well, what makes the numerator 0? Negative 2. So by setting y equal to 0, we get a solution of x equals negative 2. So the x-intercept is x equals negative 2. Now the y-intercept we find by letting all of the x values equal 0. So you could use the factored form. I'd actually recommend you use the starting form here, the more standard form, general form. So if all the x variables become 0, you're left with 2 over 3. So the y-intercept is 0, 2/3. Okay, part D is actually very closely related, almost identical to what you did in part A. Show and label the vertical asymptote directly involves your answer to part D, write the domain in interval notation. Remind me again, what's the purpose of those two vertical asymptotes? Domain restrictions. That's what x cannot equal. So what can x equal? That's what part D is asking. What is the domain? What can x equal? Everything else but those two values, 1 and 3. So in interval notation, we need to write intervals that exclude 1 and 3 but include everything else. So if you remember how to do that, it's negative infinity to 1, parenthesis, union. Is this looking familiar? Now where do I go? 1 to 3, union, 3 to infinity. So that would be the domain. Like I said, very much almost identical to the work that you had to do in part A to find the vertical asymptotes. Yeah?
Can you use the bracket again?
The bracket is if the value is included.
Okay, so it doesn't have to do with the domain restrictions. Because they're not.
Because 3 and 1 are excluded, we use parentheses because we don't want to include them. Is that what you're asking? Yeah. Yep. All right, part E is the big one. Part E, graph the function. This is where it does get a little challenging. So break it up into steps or into parts of the graph. For example, here on the right side of x equals 3, where is the graph located? Now, it can't be above the horizontal asymptote and below the horizontal asymptote at the same time. You can't have both of those pieces because it wouldn't pass the vertical line test. So either there's going to be a piece up here on the top, or there's going to be a piece down on the bottom. Do you remember how we found where it's going to be? Just plug values of x in. Yeah, random values of x. We know that x can't equal 3, but it could equal 4, or it could equal 8. You know, any of these values that's to the right. So let's choose 4. If we plug in x equals 4, that's either going to be somewhere up here or somewhere down here. So 4 plus 2 is 6. Okay, help me remember this. 4 plus 2 is 6. Down here we have 4 minus 3, that's 1. And then 4 minus 1 is 3, so we had 1 times 3. So the bottom is 3. The top was 6. So 6 divided by 3 is 2. So when we plugged in a 4, we got 2. Now, do we need to graph more points, or is that one single point enough to decide where the piece of the graph is? And honestly, the 1 point is enough because there aren't any x-intercepts right here on this side of the graph, which means that the graph is not going to cross through the x-axis or even touch it. The whole entire piece here is going to be strictly above the horizontal asymptote. So just 1 point being there tells us that that piece of the graph is completely above, like this. Now let's move to the piece of the graph that's in between the two vertical asymptotes, in between 1 and 3. So there aren't many choices. Well, actually there's infinitely many choices for x, but there aren't many whole number values of x to choose from. So let's choose x equals 2 and plug it in. Okay, again, help me remember here. If x equals 2, 2 plus 2 is 4. So we got a 4 in the numerator, yeah? Down here, we've got 2 minus 3, that's negative 1, and then 2 minus 1, that's 1. Negative 1 times 1 is negative 1, and up here we had 4, right? 4 divided by negative 1 is negative 4. So when we plugged in 2, we got negative 4. Now, it is kind of a head-scratcher here because there's not a lot of room, and there's no x-intercept in between these two vertical asymptotes. So that means all of the points in this region between have to be below. There isn't going to be any piece that's coming above because it can't cross through the x-axis. So what does that mean it looks like? It's not just going to be one single point and you move on. It's a continuous graph, so it's an upside down parabola in between there. It looks kind of like that. Now what's the deal with this piece on the left? This is kind of weird. So there's a point here, the x-intercept, and then there's a point here, the y-intercept. So we know there's a piece of the graph that's connecting the two because there's no vertical asymptote to break them up. So there is a piece of the graph like that, and it crosses through the y-axis. It never just stops at the y-axis. It's gonna continue through. Now, we've had this discussion before. As it approaches a vertical asymptote, it doesn't just stop. It either goes up to infinity or down to negative infinity. So it's already above the y or the x-axis. Is it somehow going to turn down and go like this? Why can't it do that? It only crosses through here. And it can't cross through a vertical asymptote. So there's no 0 or x-intercept here to allow it to cross through. So it has to continue on its upward path here, like that. But the question is, what does it do? What does it do here? Does it kind of bounce off and skid above it like that? Or does it cross through and come up and approach it from? Because what doesn't happen is it's not going to continue to go straight down, because that's the purpose of this horizontal asymptote, remember, is as x approaches negative infinity, the graph is eventually going to reach up here and just kind of skim along that horizontal asymptote. So it either skims along it from underneath, or it bounces off and comes back down and skims along it from above. We just got to decide what it is. So, I mean, one thing we could do is plug in negative 3. Let's see what happens when x equals negative 3. Okay, negative 3 plus 2 is negative 1. Help me remember this. Negative 1 in the numerator. Negative 3 minus 3 is negative 6. Negative 3 minus, let's see, wait a minute. Yeah, negative 3 minus 3 is negative 6. Negative 3 minus 1 is negative 4. Negative 6 times negative 4 is 24. What do we have up here? Negative 3 plus 2. So negative 1 divided by 24 is just a very, very small negative fraction, right? Negative 1 divided by 24 is a teeny tiny negative fraction. So where would a teeny tiny negative fraction be in compared to, is it above the horizontal asymptote or below? Below, but pretty close to it, like right here. So what it looks like happens is it crosses through, but it just kind of skims along that horizontal asymptote all the way to negative infinity. So crosses through and just kind of comes like that.
So they're not allowed to cross, like vertical asymptotes, but they can cross like horizontal ones?
Correct.
Okay.
They can never cross a vertical asymptote, but they can cross. But they can only cross a horizontal asymptote when what has to be there to allow it to cross through? An intercept. So if there's an intercept on a horizontal asymptote, then it's going to cross through right there. Yikes. Next one, number 5, is the same topic. Just a few different ways of doing it. Well, you'll see. Show and label all asymptotes, intercepts, holes. So let's do it in the same order. If we wanted to do the vertical asymptotes, we would need to, I don't know if you guys can see that, but x to the third minus x squared minus 6x, how's that going to factor?
Factor in x out.
Okay, so if you factor out an x, x minus 3x plus 2. And then the numerator also factors into x minus 1, x plus 2. I made very small mention of something like this in section 3.6. I didn't include this next part. I didn't include in the Unit 2 exam. It was just kind of a brief mention on your notes. But do you notice anything peculiar about this one that didn't happen on question 4? It's got common factors, right? You seen that? Common factor x plus 2 over x plus 2. They do cancel out. The x plus 2 cancels out. But let me ask you a question. Before I cancel it out, before I do any simplifying of this, is it okay for x to equal negative 2? In the original form of the equation, is it okay for x to equal negative 2? So what would you say about x equal negative 2 and the domain? Is x equal negative 2 in the domain? No. Y'all follow me on this? Negative 2 is not in the domain because you can't plug in negative 2 right here, you'd get 0. However, when you simplify, it would now appear that x equals negative 2 is fine, but that's not the case. When you're deciding the domain, you have to decide the domain based on the original function, which is this. Okay? So again, one more time, is it okay for x to equal negative 2? No. But when you make the simplification here, you decide what the vertical asymptotes are going to be based on the simplified form. Okay? So we are going to now decide what the vertical asymptotes are on the simplified form. So how many vertical asymptotes are there going to be? 2. There's going to be 2 vertical asymptotes. But in the back of your mind, when we start graphing this, I want you to remember there is still one more excluded value. What is that? X cannot equal negative 2. So just remember that here in a second. But
So you don't graph that like an asymptote?
no.
You do include it in the domain, you do exclude it from the domain.
Correct.
Oh, that's tricky stuff.
So-
Open circle.
So why would you do that? Why wouldn't you add it as on the graph as a vertical asymptote?
Because you exclude it a different way. It's called a removable discontinuity. We removed the discontinuity, so it's still a discontinuity. A discontinuity means when you're graphing the graph, you have to lift up your pen or pencil to start a new piece of the graph somewhere else. And that's what a vertical asymptote does. It separates two different pieces, right? There's another way of doing that without using a vertical asymptote. And you use that if it's called a removable discontinuity like this one. We removed x plus 2 factor by simplifying it. So the only two vertical asymptotes are, what's this one here? 3 and 0. So let's place those vertical asymptotes. So we have one at 0, and you would label it x equals 0. And we have one at 3. So you'd label it x equals 3. Okay, so there's the vertical asymptotes. Now, oh dang, this one is actually the same as question 4. I thought the horizontal asymptote would be different, but it's the same location because this is degree 2, this is degree 3, so obviously the numerator has a smaller degree. Do you remember what happens when the numerator has a smaller degree? It's equal to 0. So let's talk about what would happen if they were the same. So let's say that this was x squared and this one was also x squared, because that happens a lot. What if they're both the same degree? Do you remember what happens there? You divide their leading coefficients. So that's probably something to note on your review here. If they're the same degree, then you divide their leading coefficient. So let's imagine that these were the same degree. The leading coefficient here is 1. The leading coefficient here is 1. So 1 divided by 1 is 1. So in that case, the horizontal asymptote would be up 1 unit if they were the same degree. These, however, since the numerator is smaller, is going to be the same as in question 4. The y, or the horizontal asymptote, is the line y equals 0. If the denominator is smaller, there is no horizontal asymptote. Okay, so we did the vertical asymptote, we did the horizontal asymptote. Let's do the intercepts. We're going to find the x-intercept like we did the last problem. We're just going to set the whole thing equal to 0 and solve. So looking at this one even, if this is equal to 0, that's only going to occur when the numerator is equal to 0. So x equals 1 is an x-intercept. Yeah. Now before I forget, remember in the back of our minds we're keeping in mind that negative 2 doesn't work. It's excluded from the domain. But where is that on the graph? So if we were to plug in negative 2, help me remember the values here. Negative 2 minus 1 is negative 3. Here we have negative 2, and then that's going to be negative 2, so that's negative 5. Negative 3 minus, so negative 5 times negative 2 is 10, and then up here we had negative 3, so negative 3/10. That's like negative 1/2 almost, negative 0.5, a little less. So when I plugged in negative 2, I got negative 3/10, which is right about where my finger's pointing. Would you agree? It's excluded from the domain, but we're going to treat that different than these two vertical asymptotes. What happens when you have that removable, it's called a removable discontinuity when you can cross out common factors like that. You put an open circle at that point. So I'm going to put an open circle at the point negative 2 comma negative 3/10. And the graph is going to pass through that open circle. That open circle just represents that there is no value at x equals negative 2. It's excluded from the domain. It just behaves differently than the two vertical asymptotes. Okay, now what's the, what did we forget in the no, let's see, what did we not do?
You got that one as the x-intercept or the y? Yeah, it's the x-intercept.
That's the x-intercept.
X-intercept,
Yes.
because we solved, if this were set equal to 0, the only way that would happen is if the numerator is equal to 0.
Gotcha.
We didn't find the y-intercept. Is there going to be a y-intercept?
No, because there's a vertical asymptote.
There's a vertical asymptote right here, so there isn't going to be a y-intercept because of that vertical. There can't be a point that exists on the y-axis because there's a vertical asymptote there. So no vertical asymptote. And if you forgot that, then what was the other way that you could try to find the y-intercept?
Set x to 0.
Let x equal 0. But if you let this x equal 0, 0 times that is 0, you can't divide by 0, so you wouldn't be able to find the y-intercept anyway. Okay, now let's... in the directions where it says label all asymptotes, intercepts, and holes, that's what this is. There's a hole in the graph right there. That's what it means by find all the holes in the graph. And I'll just piece the graph together. Let's start on the right side again. To the right side of x equals 3, we can plug in x equals 4 to determine whether it's going to be above or below that horizontal asymptote. So if I plug in a 4 here, 4 minus 1 is 3 in the numerator. 4 minus 3 is 1, so 4 times 1 is 1. So we had 3, yeah, 3 fours, right? So we plugged in 3, we've got 3 fours. So 3 fours would be about right there, which means that piece of the graph looks kind of like that. In between the two vertical asymptotes, there could be a lot of options. It could kind of be a parabola where it bounces off and goes up in both. It could be underneath and bounces off like that, or it could start up here and cross through, or it could start down here and cross through like that. Lots of different ways this could happen. What do you suggest?
Plug in 2 for x.
Let's plug in 2. Let's see what happens when x is 2. Okay. 2 minus 1. Let's see. 2 minus 1 is 1. And then 2 times 2 minus 3, so that's negative 1. 2 times negative 1 is negative 2.
Negative 1/2.
So we had 1 here and negative 2 here, right? So that's negative 1/2. So when I plugged in 2, I got negative 1/2. Now that's not super definitive. It could still be where it comes up like this and touches there and comes back down here. I mean, I guess that's a possibility. It's more likely that it comes up like that, but you don't want to take a chance. What's the safest way to do this? What if we plugged in 0.5? And here's an easy way to do this. It really doesn't matter what the value is. All that matters is a positive or negative. That's really what's important at this point. So if you plug in 0.5 to the numerator, are you going to get a positive or a negative value? Remember that, negative, right? Because 0.5 minus 1 is negative. Now if I plug in a 0.5 here and here, 0.5 minus 3, is that positive or negative? Negative, but here it's positive. A positive times a negative is negative. But then a negative divided by a negative.
Positive.
So when I plugged in 0.5, the value isn't important. It's what it was, positive or negative. What was it?
Positive.
Positive. So it's some positive value above the x-axis. So what does that tell us? It's above it here, and it comes and crosses through like that. Now, there is an exclusion from the graph here, but that does imply that the graph extends to the left and to the right from this point. So we can kind of infer that the graph is down here in this bottom corner because there's already a hole in the graph down there. But if you don't want to just assume that, how else can you find out where the graph is here? Plug in any other point besides negative 2. So what if we plug in negative 1? And if you want to do it quick, just focus on negatives and positives, not actual values. Negative 1 minus 1 is negative, right? Negative 1 here, and then a negative 1 minus 3 is negative, but a negative times a negative. So this is positive. Up here was negative. A negative divided by a positive is negative. So when I plugged in negative 1, I got some negative value, which means it's coming down like this. It skips through that point and comes like that.
So it just skips over that one part and continues going as it
Mhm.
And even though it's a horizontal asymptote, we can just assume that it's going to like continue to negative infinity without crossing it, or do we?
It can't-
does it matter?
It can't cross through because there's no x-intercepts over here to allow it to cross through.
Oh, okay.
Does that make sense?
Yep.
Okay, that's it for Unit 2.